Hello everybody, welcome back to another basics video from Wild Shrimp. Today we're looking at pH, and before you click off, no, we're not going to do what every other video has done. If you need pH 6, that's saltwater, that's better for these fish. We're not doing that, okay? That's not how we roll here on the basics series. We're going to look at what pH is, where it comes from, why the numbers are 1 to 14, where the numbers are derived from, what can impact your pH, and, well, why neutral may not be the number you think it is. So pH, where does it come from? It came around in 1909. There was a Danish chemist who basically invented pH. His name was Soren Peter Leibniz. No, that's a biscuit. Soren Peter Lauritz Sorensen. So, pH. pH is the measure of free hydrogen ions in a solution. It was invented by this Soren guy in 1909. And what the H stands for is quite clear. It's hydrogen. Okay. But the P is something that a lot of people can't agree on. A lot of people will argue to the death, I believe, that the P is derived from a German word for power. They will argue that it is a derivative of a French word for potential, the potential of hydrogen, the power of hydrogen. Some people will argue that it is just P, because P is used in chemistry so often in experiments that he just put pH, experiment of hydrogen, because that's what he was doing before he discovered it. He was experimenting, testing for it. Which kind of makes sense. However, who cares? Doesn't matter. That's just where it came from. Scale of 1 to 14, 1 being low, 14 being high. What does that mean? It's the measure of free hydrogen ions in that solution. Now, we call 1 to just under 7 acidic, and we call just over 7 to 14 basic, not alkaline, from the Arrhenius theory. But what you need to understand is that whilst all alkalis are basic, not all bases are alkalis, okay? Because an alkali is specifically a base that is soluble in water. It dissolves into water, all right? And although in the aquarium trade or the aquarium hobby, we are only really dealing with stuff like that, and therefore comes under the Arrhenius theory of what acids and bases actually are, because there are 3 theories, believe it or not. We should, I believe, be referring to them as bases, because especially newbies, and maybe you're one of them, you hear alkaline and then you hear alkalinity and you think, well, they're the same. No, they're not. They interact quite a lot, but they're not the same. So I really do think we should just be referring to bases as bases and not alkalis, even if we are dealing with alkalis. Okay, just to try and avoid some confusion. Now, on this scale of 1 to 14 that you're looking at, what you don't see very often is another scale that runs from 14 to 1 or 1 to 14, depends if you're looking at it in a mirror or not. Now, that scale that runs opposite to pH scale is the pOH scale. So we've already discovered or talked about, or I've told you if you didn't already know, that pH is a measure of hydrogen ions in a solution, while pOH is a measure of hydroxide ions in a solution. Hydrogen ions have the chemical symbol called H+, and hydroxide have OH negative. Okay? H plus pH, OH negative pOH. Simples. They run completely opposite. And the reason I'm telling you about pOH is if you're going to go and do some research, you're going to look into scientific papers, things like that, like I did for evidence on the Not Another Brine Shrimp video, because are they really such a great source of protein? If you haven't seen that, check it out, by the way. It's not everything that you think it is, brine shrimp. However, pOH, they're not the same, okay? But you can, if you're given a pOH value, you can figure out your pH value. You subtract your pOH from 14, that gives you your pH. All right? Dead simple. So these numbers, 1 to 14, yeah, we're still on the scale. Each whole number represents an exponential increase in hydrogen ions, or decrease. Depends on which way up and down the scale you're going. Okay, it's logarithmic. Because it's logarithmic, a drop of pH from 7 to 6 is not 1. It's actually a factor of 10. So 6 is 10 times more acidic than 7. 5 is 10 times more acidic than 6. So next time you think about plopping and dropping, by the way, that's backwards. Who came up with plop and drop? You have to drop it before it plops in. It should be drop and plop. If you're plopping and dropping, you're either in a time warp or you're upside down. I'm not sure which one it is. But if you are plopping and dropping, as the hobby normally refers to it as, if you are plopping and dropping a fish into pH 6 that is coming from pH 7, you need to understand that you're subjecting that animal to water that is 10 times more acidic than it's coming from. Now, the difference between pH 5 and 7, it's not 20, okay, because each one is 10. It's logarithmic. The difference between 5 and 7 is 5 is 100 times more acidic than 7. If you didn't know that, now you understand why pH shock can be a very real thing. It doesn't have to be as low as 5. If you're putting them into 6 and they're used to very close to 8, you're getting on for 100 times more acidic. I don't think we'd like that. Now, under the Arrhenius theory, acids in water give off hydrogens and bases give off hydroxides. So if one has more acids, it's an acidic solution. If it has more hydroxides, it's a base solution, okay? Neutral is only ever when both of those are in equal numbers. Now, that may not be the number that you've got in your head, all right? So if the numbers are equal number of hydroxides and hydrogen ions, then we're talking neutral. Now, because we are talking about aqueous solutions, water in glass boxes, we can't really refer to them as hydrogen ions anymore, okay? They are known as hydronium ions. And that is because hydrogen ions cannot exist in water. They are bonded to the H2O molecule and you get a hydronium molecule, which is H3O+. H2O plus the extra H makes H3, and because it's now positively charged because of the extra hydrogen, which means it's no longer balanced, it has a plus symbol. So H3O is H2O with an extra hydrogen and positively charged. Look at those numbers. What do they mean? They are numbers of hydrogen ions, and that is the measurement of moles per liter. All right? And that is what it is measured in, moles per liter. So 0.000001 is the same as 1 times 10 to the power negative 7. Okay? 0.0000126 is the same as, so I'm having to hold this, 1.26 times 10 to the power negative 7. Right? And that will go on all the way down here. This one is 5.01 times 10 to the power negative 7. This top number is also known as pH7. This number all the way down at the bottom is known as 1.0 times 10 to the power negative 6. This is pH 6. This is pH 7. This is pH 6. This is 6.9, 6.8, 6.7, 6.6, 6.5, and so on and so on. Now, those numbers will never change. There's some rounding up that goes on, obviously, because this number is long as hell. But that is 6.8. That is 6.7. It's logarithmic. Remember, every jump is 10. So if we take out one of these, that number, count the zeros after the decimal point, is the same as 5.8 or 1.58 times 10 to the power negative 6. Get it? See why we've got blocks of 10? Because this one has 6 zeros at pH 7, and to get down to pH 6, we have 5 zeros. So this one is the same as this one, but it has increased by tenfold. Remember your basic maths? You know, these are units, tens, hundreds, thousands. It's increased by a factor of 10. You follow it? So, just to make it a bit easier, a bit bigger, easier to see, this was one of the numbers from the last page. It is this, 501 times 10 to the power negative 7. Okay? It is also known as pH 6.3. Now, if we increase the number of hydronium ions by a factor of 10, we get rid of one of those, which is just the same as moving that decimal place this way one. We have 5 zeros, and the pH becomes 5.3. We get rid of another one, becomes 4.3. That number will stay the same. This will change. That would be -6, -5. But that is how the pH number that you look at, 6.3, 5.3, 4.3, comes about. That's why they're like that. That's why it's logarithmic. That's why it's exponential. It's all in the maths. Now, to work out those numbers, to find your pH, all right, you would negative log and then H3O plus, which is our hydronium ion. Yeah? So if you have a pH of 6.5 and you want to know how many hydronium ions are in there, you substitute your pH for 6.5 minus log H3O plus gives you 6.5 is that number there. 0.0000001,316. All right, so there's another number. 1 times 10 to the power negative 14 is the same as this long number, 0.13 zeros and 1. What is that? Looks like pH 14, right? No, this is special. This is kW. Now, what kW actually is the rate of dissociation and association that water goes through. So kW is the ionic product of water, which is the equilibrium constant for autoionization. So if you have a glass of water that looks very, very still, there's no movement in there. Whilst it's sat there seemingly doing nothing, there is an entire universe of hell activity happening in there. Every molecule of water is dissociating an H plus ion or an OH negative ion at the same time. The same number that are getting rid of H plus, others are getting rid of OH minus at exactly the same instant, at exactly the same volume and quantity. That is how equilibrium comes about. Because to be neutral, the OH minus value has to be the same as the H plus value, right? That's what makes it neutral. Now, earlier we asked about what is neutral. Maybe it's not the same as what you think it is, and the number in your head probably was 7. Now, if you've ever seen on some test strips or test liquid test kits, they have a band of what they call neutral, 6.5 to 7.5 quite often. And that's because that's right and 7 is wrong. Now, don't get me wrong, pH 7 is neutral, and that is neutral, but it's not always pH 7. That is because that is the rate of dissociation and association of H plus and OH minus at 25 degrees, otherwise known as 298 degrees Kelvin. So, if that is equal, and that only happens at temperature of 25 degrees Celsius, for pH 7 to be neutral, pH 7 is only neutral at 25 degrees Celsius. Now at 37 degrees Celsius, the pH is actually around about 6.81. That's neutral. That is chemically neutral. Forget 7. But look how many times more acidic that is than 7. 6.8. It's quite a lot. Now, at 37 degrees C, the pH is around 6.81 when it is chemically neutral. And that is because the 1 times 10 to the power negative 14 has become 2.4 times 10 to the power negative 14. Now, let's not get into the fact that there's no such thing as cold and only a lack of heat. Let's not get into that. That's not what today's video is about. But these two, or you could say that this is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 2, 4. They're the same. Okay? But those are neutral. 6.81 at 37 degrees, water is neutral. Now, you're not going to be running your fish tanks at 37 degrees unless it's one of those crazy fish from literally boiling place. I can't remember what that's called. They're not for me. I'm not going to be keeping them anytime soon, so let's not worry about those. So the entire time that your water is sitting there, producing and sort of using or removing OH negative or H plus ions, as long as the numbers are exactly the same, happening in the same instant, you have a neutral pH. But to maintain a neutral pH, no matter what the pH number is, those numbers of association and dissociation can never exceed each other. They must always remain the same. At no point can they come out of balance. Isn't that incredible? So to basically summarize KW, the higher the temperature is, the lower the pH value is of neutral water. So at 37, we have 6.81. At 25, we have 7. Now you're thinking, well, that minus 14 to the power minus 14, how does that relate to pH? Because we're talking about pH always being, you know, up to 7, acidity is up to 7, and basicity is down to 7. Well, if we have 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, if that is the same as 1 times 10 to the power negative 14, we have to remember that Kw is, like we've discussed, the sum of H plus and OH negative. Okay, that's what Kw is. Now, if that number is this, because Kw is this, this, and this equation, 2 elements have made up that number. And for those 2 elements to make up that number, they must be in equal value. So to find out neutral pH at this, all we need to do is what is the halfway point. What is the value of these 2? So we just square root it. What number times by itself, because this number times this number creates that number, so we end up with pH 7 at this rate, which only occurs at 25 degrees Celsius. Oh, nearly dropped that. And because pH 7, the way we get to it is 0.00000001. Okay, that is pH 7. So 1, 2, 3, 4, 5, 6, 1. And that is right in the middle. And that is the only reason that pH 7 is neutral, because of Kw, the constant equilibrium of OH and H at 25 degrees. That's pH. That's why it's minus 14 when we're looking at KW, because it is the sum of the POH and the pH combined. KW is OH negative and H plus at the same time in equal value. Quite simple when you think about it. Now, let's move on. What can affect your pH other than temperature? So I've lost the lid for that. Where the hell is that doohickey? Well, that's lost and gone forever, oh my darling Valentine. Now, people will tell you that wood and Indian almond leaves, catappa leaves are botanical range. Drop your pH. They do, but very, very slowly. And they can only do that if they can overcome your KH. Now, we're not going to discuss KH, but KH is the alkalinity that you may have heard about and been rather confused about. An automatic feeder has not been turned off, and it's not actually on an aquarium at the moment, and it's just going round and round and creating a mess on this shelf. So brilliant. How do organic things break down and lower the pH of your water? So organic breakdown is not only the leaves or the woods, the botanicals, it's also the food and dead rotting bodies in there. And it's quite simple. They do that because they release the ions, the hydrogen plus ions. If the hydrogen ions, the free hydrogen ions, the acidity is the charging Romans, your portcullis on your castle wall is your KH. Until they wear through that, this acidity can affect the water on the other side. Okay, best I can come up with, short notice. So once you've got enough acidity, free hydrogen ions, or hydronium ions as they now are because they're in an aqueous solution, you can wear away the KH. And once you've done that, as the KH drops, it allows more acidity to take a hold on the water. So something else that can drop the pH of your water is probably one of the biggest ones and the most commonly used and least understood: CO2 systems. Carbon dioxide injection. Carbon dioxide is 200 times more easily dissolved into water than oxygen is. This is why RO water, when it first comes out of the machine, is a very low pH, because it grabs the carbon dioxide out of the air essentially much faster than it can gas off when it takes on oxygen. So if you're storing RO water like we do, it will eventually gas off and you will have a much more neutral pH, around about 6.8, 6.9. If you use it immediately, it will have its pH 5, 5.5. But if you're adding it to a tank with an air stone, it's going to gas off that carbon much quicker, which means your pH is going to rise. So if you're using RO water for stability, if you are really hell-bent on stability, genuinely do recommend that you store it before you use it. Give it a chance to sort of settle out. Now, when you're injecting carbon dioxide, what happens is the carbon, it dissolves, which is called dissolution, into the water, and it forms carbolic acid. Now, because it's an acid, it dissociates its hydrogen atom, hydrogen ion, as covered by the Arrhenius theory. It dissociates into H plus and bicarb. So what you actually end up with is your H plus ion buggers off, and you end up with HCO3 negative. All right, and that is basically acidifying your water, and it's doing the same thing to your KH as it did previously with the wood and the organic stuff. Now, you have to be very, very careful. You'll notice that people with carbon injection often have a timer set on it. And this is because pH values can fluctuate throughout the day. Doesn't necessarily, it happens whether you have carbon dioxide or not, right? And that's because if you have live plants, whilst they are taking in carbon dioxide and giving out oxygen during the day, when the lights go out, they do the opposite. They give out carbon dioxide. Now that is lowering your pH. So if you have a lot of live plants, regardless of whether you've got CO2 or not, check your pH first thing in the morning, as the lights come on, and then just as they go off. You see a difference. And that is because whilst the lights are on, they've been using up the carbon dioxide. They've been sort of raising the pH of your aquarium. Now, this can erode your KH over time. And this is why sort of like an old tank syndrome, tank crash can happen. If you've got live plants, wears out your KH over time. This is why water changes to keep your KH stable are important overall, keeping your pH stable. So, when you've got it with carbon dioxide injection, that is just exponentially bigger impact. If you're injecting CO2 during the day, that's okay because the plants are uptaking it. You don't want to be doing it at night because the plants are giving it off, they're not using it, and you're injecting it. pH crash or potentially just hypoxia from the fish. It's not that complicated if you know what you're doing. We don't use CO2 because we're really here to breed fish rather than have beautiful planted tanks. So if that's something you're interested in, go and speak to somebody who runs a lot of CO2 on their planted tanks, and they will talk you through it. Some people turn their CO2 on an hour before the lights come on to build up sort of like a reserve in the water for when the plants are ready for it, and they'll turn it off an hour before the lights go off. That's quite common to see. But yes, so those are a few things that will affect your pH reading. For best effect, try and take your pH readings at the same time in the light cycle. Doesn't matter what time of day, it's dependent on your light cycle, when the tank is exposed to light. If you want to take a constant monitoring of your pH, do it at the same time every day.
Now, obviously, not all fish want soft water or low pH. These little marine things we found in a rock pool whilst we were away on holiday, and the little one absolutely loved, like quite hard water. So how do we go about that?
Okay, I apologize for the huge continuity error, but we lost all this footage. And it would be this bit, because this is the most foreign piece to me. So this is like speaking Japanese, because I fight so long to keep my pH down, because we have quite a hard water at the tap here. That having to go over this again is just great. But trying to raise your pH. What do we quite often use? Crushed coral, aragonite, limestone. Now all these things have one thing in common, and that is CaCO3, calcium carbonate. Calcium carbonate, how does that help us? Well, the anion part, which is actually would be CO3 minus, reacts with the free hydrogen ions, which we talked about earlier. Now, this is what causes the water to be acidic, right? Well, this binds to those, removing those, so they're no longer free. And you end up with H2CO3, okay? That has hoovered up these, meaning there are no more free hydrogen ions, which essentially raises the pH, because this is what the triggering factor in lowering the pH is. We following? So what is this? This is carbonic acid. Acid, but carbonic. Now this is a makeup of two things we're very familiar with, and it breaks down back into those two things. Now this is essentially the same way that Seachem's acid buffer works. If you have hard water, you add this chemical, which they give you, and it breaks this stuff down into still the H's, still one O, and that leaves us with a C, an O, and a 2. So carbonic acid breaks down into water and carbon dioxide. And the cycle will just continue, because carbon dioxide in water, well, guess what it forms? Okay, so calcium carbonate is not actually that soluble in water. To be more soluble in water, it needs to be calcium bicarbonate. Now, earlier we had some CO2 left over from the carbonic acid. Now we're going to need that, because the actual calcium carbonate is much more soluble in water that has CO2 in it, because that becomes calcium hydrogen carbonate, or calcium bicarbonate, which is much more soluble in water, and actually happens to be the conjugate base acid. It's the conjugate base for carbonic acid. So it can really hoover up these free hydrogen ions. And that is essentially why the pH rises. It will also increase your KH, because when you've broken down, remember we had the Ca at the beginning of the CO3. Remember this bit? Well, this is the bit that we used earlier, but we are now still left with the calcium. And what this will do is it will go on and it will mix with the anions of other acids, and it will form a salt, an inert salt. It will be balanced. So there'll be no pluses or minuses eventually at the end. And that's what affects your KH. Okay, so your carbonate hardness is linked to pH, and they sort of interact with each other in several different ways in the aquarium. It's not something that I pay a massive amount of attention to. I'm very lucky because I keep a lot of soft water fish, and essentially just keeping a KH of anywhere between 2 and 5. These fish do great, and that comes quite easily by mixing RO and our horrendous granite tap water. But hopefully that has given you some idea of how it works to lower your pH and raise your pH, what pH actually is, being, you know, POH or pH, the hydrogens or the oxides. So that is what I've got on pH. Sorry about to redo this bit, and it's delayed it quite a lot. But yeah, hopefully that has given you some sort of basic understanding of pH. It's not quite as straightforward as a lot of people think. And let's start calling alkalis the proper term, shall we? So I'm going to see you in the next one. I've got a delivery of fish coming at some point today, and we're going to do an unboxing on that, because some of you maybe haven't seen or haven't had the courage to experience what it's like to receive an online fish order. But these guys I trust. I've had lots and lots of deliveries from them, so I'm looking forward to that. And until I see you in the next one, try and find a reason to make somebody smile today. Just quickly, before you go, I realised I've been a bit of a shit and I haven't balanced the equation, and it's a lot easier for some people to understand it. So, calcium bicarbonate, okay? Calcium HCO3, 2 sets of. So, we've got 1 lot of calcium, we've got HCO, 3 O's, but 2 lots of that. So there's 2, 2, 6, essentially. So in calcium bicarbonate, we have our calcium carbonate, which was this, yeah? So we've taken our first set of 3 oxygens down to here, 1 of the C's of which there are 2, down to here, and our calcium. Then we are going to take another one of these C's, because there was 2, remember. We're going to take 2 of the remaining 3 oxygens, and 2. That gives us our carbon dioxide. And then what are we left with? We are left with the 2 H's and the remaining oxygen. So essentially that is balancing the equation of calcium bicarbonate. So I hope that, if I've confused and discombobulated everybody up until that point, hopefully that sort of levels it out in your brain. I don't know. Sometimes my brain just needs leveling. Ideally not with a brick. But yeah, that's what we really have got, and I will see you in the next one.